Okay, next we're going to talk through some sample problems from your 4.5 homework. And we're going to do a series of questions that ask you just what would be the first step if you were going to solve this. So you may have some homework problems that just say, how would you start this? All right, so conceptually, what's the first step if you're going to solve 10 to the x equals 40? And we've done stuff like this before where you're trying to find what exponent is needed, 10 to what power equals 40. And we've talked about how if you can't make these like bases, then you want to take the logarithm of each side. That's exactly what a logarithm will do. It'll solve for the exponent. Solving for the exponent is, in essence, doing a logarithm. So you could take any base log that you want, but we have two buttons on our calculator, an log common log button and an ln natural logarithm button. So if we're doing a 10 here, the better log, just a little easier calculation, is to take the log log, the common log. So that's going to be your answer to that question if asked, is what's the first step? Take the common log. When you do take the log, and you may not have to actually solve this, but I just want to demonstrate, it brings the exponent down. X times log 10 equals log 40. Now, log 10, the reason we kind of recommend doing the common log is log 10 will be just 1. It'll come out even since it is a power of 10. Remember, log means the base. This is a base 10 common log. 10 to what power is 10? So 10 to the first is 10. So it just reduces a little nicer and becomes x times 1, or x equals log 40. Then we can simply type in log 40 on our calculator to get the answer. All right, so the common log would be the easy way to do that. Okay, this next one says, what's the first step for this one? So since the base is e here, ln, the natural log button, ln logarithm, works well with e. They play well together, I might say. So ln, I would take the ln of each side, and then that brings this exponent down as a multiplier, 6x minus 1 times ln e equals ln 29. So ln e, you'll find this on your calculator, means base e. Anytime you hit the ln button, it means you're doing a base e log. Just like log means a base 10 log, ln means a base e log. So it's saying e to what power is e. So once again, that comes out to be 1. ln of e is 1. To do that on your calculator, it would look like this. You would find your ln button, ln, find e on your calculator. Some calculators have an e and an e to the x. Let's see if I can show you here. My calculator, which you don't have to use a graphing calculator, this will be true on any type. It has an e button, just regular e here, and it also has an e to the x. So if I'm just wanting to type in regular e here, I do second function of that. Close that parenthesis, ln of e, and notice that's 1. Now, if you only have the e to the x button, I can also do that. I'll do ln, I'll do my e to the x button, but I'll need to tell it I'm doing just e to the first, just regular e, and close that. That would also work. Now, if you're using the other type of calculator, I mentioned maybe in another video, a regular scientific calculator, some of those type in just the same as what I just did here, but some kind of work backwards. And to get your e to work on this, your e to the x button, you have to type in the 1 and then the e button to get e to show up. There's e to the first power. It's about 2.71828. It goes on and on. It never repeats. It never terminates. It's an irrational number. So you might hear it called irrational e. So e to the first power. Now this calculator, let's look through our keys. I don't know if it has a regular just e without an exponent. I do not see it. So some do, some do not. And do not worry if it does not. But again, e to the x, make it the first if you're trying to get regular e. Then if I did that, if I button there, but anyway, so type in the x first and then hit your button. So e to the first, I hit 1, and that's what e to the first would be. All right, so that's how you'd work there. So like I said, ln and e play well together because the ln of e is 1, and it just makes it easier. You could do it the other way though. You could argue that if you wanted, and then complete your work. ln of 29 could be worked out on your calculator. Again, if I'm using this calculator, I'm going to hit, let's see, ln. See, it won't let me hit ln directly. I have to hit the 29 and then the ln button. So notice that. Whereas on this calculator, and in other scientific calculators, they're all just a little different. I hit the ln button and type in 29 equals, and it types it in kind of in order, ln, and then type in the 29. Where this calculator, same answer, but I had to hit the 29 and then hit the ln button. So just be aware of how your calculator operates. Okay, next question. Just asking what would be the first step. And in this problem, it has a logarithm already in it, and a base 4 of an argument equals 18. 18 being the exponent. Remember, the meaning of a log is this is the base raised to that exponent to equal that value. So the first thing I would do, the first step, is take it out of log form. When there's only one log in the problem, that's usually the first strategy is to rewrite it, change it to exponential form. To do that, we would say 4 raised to the 18th equals the argument x squared minus 10, and then we would work that out. It is 4 to the 18th is a large number, by the way, so whatever 4 to the 18th is, and maybe that's why this one is just saying just how would you work it. You can then 10 across the line, whatever 4 to the 18th is plus 10 equals x squared. Work that out, and then you take the square root of each side to finish, but it didn't really ask us to do that. Okay, and then another, just what is the first step? Here we have E, which like I said earlier, E is just a value. It's about 2.711. So it's not a variable. E is not a variable. The X is in this problem. So we have like bases. And you know, when we have like bases and we're multiplying, we can use the product rule for those exponents. We can say like bases multiplied, you add the exponent, 6x plus x. So we would add that, making e to the 7x equals 10 to the e, and then proceed. All right. Another, what would you do first? What's the first step? Not necessarily solving it, but what would you do first? Here we have log in expanded form. We have log, and it's a base 10 log of this argument, plus a log and a base 10 log, again, of an argument equals 1. So there's not a log on this side. You could, and you could argue this, you could try to make this side have log in it as well, so it would have logs on each side. But of the choices that were listed for this, it said write the sum of the logs as a product to change this side into just one log. So this is an expanded log form, and you do have like base 10. So to condense that down to one log, you can say that multiply and add go together in the exponent rules, and logs are exponents. So we can condense this expanded form into one log, and then because in expanded form it's plus, those become multiplied in condensed form. All right, and then we can proceed whichever way you want. You can make this 1 into log 10 if you wanted, and then take the logs off of each side. That's one strategy. Or what we just did on our last example is we would say take it out of exponential form, write it as or take it out of log form and write it as an exponential form. So we'd say 10 to the first equals that. That also would give us the answer, or the next step to get to the answer. And then we'd proceed with our steps. Okay, number 10 then. This example, we actually are going to work this out. Now that we've kind of went through all the first steps or how to proceed process-wise, now let's just work some problems. So to solve this problem, we have different bases. There's no way to make a 3 and a 7 into like bases. No easy way to do that. So we take the log of each side, which can be log or ln. I'm going to do ln logs. That brings your exponent down as a multiplier. X times ln 3 equals, and if there were an exponent there, I'd bring it down, but there is not. So just write ln 7. ln 3 can be computed at any point, but it's a decimal number, so it's a long decimal. But notice ln3 is about 1.098612289, and it keeps on going. It never repeats, it never terminates. So we don't want to have that messy decimal on our paper, and we might have round off error if we do. So we avoid changing these values to their decimal value until the very end until we have to. So I'll just know that that's x times some constant. So if I divide that on this side, I'll divide it on this side, and then I'll be able to solve for x. Now I'll type that in my calculator carefully. I'll say ln of 7, make sure you close your parenthesis, divided by ln of 3, close that parenthesis, and then it'll be exact, and then I can round to the whatever decimal point they say. If they say the 4th decimal place, then the 4 would not round it up. It'd be 1.7712 if asked for 4 decimal places. Okay, number 11. Example 11, it's really the same question. You can do the same thing we just did there. Take the ln of each side, just with different bases. When you take the log of each side, it brings your exponent down. X times ln of 1/5 equals ln of 10. And same issue here. We probably just don't want to see that ugly decimal, so I leave it intact and say whatever ln of 1/5 is, I'm going to divide that on this side, divide it on this side, and then x will be, and I'll type that in my calculator, ln of 10, close your parenthesis, divided by ln of 1/5. Okay, and that's negative 1.430. I'm going to round that to 7 if I'm doing 4 places. Okay, number 12, same concept, but just a little more with the decimals to give us more steps to do, but it's the same concept. So we take the log of each side. That brings this exponent, which is now a quantity, x minus 3 exponent times ln of 2. Bring this exponent down to x times ln of 3. Now, again, we leave these intact, but know that is just a constant. So what do we do when we multiply by constants is we distribute. So we'll have x times the ln of 2 minus 3 times the ln of 2. And that will give us 3 terms. We've got this is a term, this is a term, this term, this term. 3 terms. We want to collect our x's to the same side and then our constant to the other side, just like we always do in solving algebraic equations. So we'll bring this x to the left and this constant to the right. So rearrange your terms. And I'll have x ln of 20 minus 2x ln 3. And that will become a positive 3 ln of 2 when I move that to the right side. Now, the best way to do it to keep it most intact is to factor out the x from the 2 terms, the 2x terms. All of this stuff here could be, again, typed in our calculator if we wanted to, but just in your mind know that is some calculation we could do at any point, but we try to save the calculation to the very end to keep it intact. And then it's a trick to get this in your calculator, so carefully put this in your calculator. We always have to tell our calculator where the numerator is, so we need a parenthesis around the numerator and a parenthesis around the denominator. Then there's also a parenthesis around the argument of the logs, so you'll see some places where you'll wind up with a double parenthesis. So how does that look when we type it in? All right, carefully typing this in. So parenthesis 3. And whether you have to put a times sign or not is kind of up to your calculator. Some do and some don't. Then open parenthesis for the denominator. Make sure you're closing any open parentheses. Close, close. All right, calculator says negative 1.3825. So depending on the decimal place, I'm going to say the 5 is the 4th place. The 3 won't round it up, so I'll leave that off. It's negative 1.3825 for that calculation.